First, let us discuss the preliminary steps before moving on to the estimation of the VECM model. It is not necessary, but generally helpful to apply tests of stationarity on the variables before Johansen's test and VECM. We know that cointegration cannot exist in stationary variables. If tests of stationarity such as the ADF test show that variables are stationary, we don't need to go through the procedure of estimating VECM. Similarly, if the variables are integrated of order 2 or the variables have different orders of integration, we generally avoid the VECM model. Therefore, if we can determine that the variables are I1 or integrated of order 1, we can go ahead with the procedure of estimating VECM. The first step is to plot the variables and see which trend specification might be appropriate. We already discussed the commonly used trend specifications in VECM and when to apply them in Tutorial 4. To illustrate, we will plot the variables in the Denmark dataset used by Johansen and Giselius in their VECM paper in 1990. The data contains 5 variables on log of real money, log of real income, log of price deflator, bond rate and bank deposit rate. Let us take a look at some of the plots of the variables. The first plot here is for the variable LRM or log of real money. The second plot shows the variable IDE or bank deposit rate. If we look at the plot for IDE, we don't see a deterministic trend, which was also the case for IBO. In case of the variable LRM, it seems to be moving upwards. We observed the same situation for the variable LRY. However, the trend does not seem to be deterministic in nature. We can surely eliminate the unrestricted trend specification because there are no quadratic trends in the variables. Similarly, the no trend or constant specification does not seem plausible because we don't expect the long-run relationship between real money, real income, bond and deposit rate to be stationary around zero mean. We will need a constant in the long-run cointegrating relationship. We won't need to include a trend in the cointegrating equation because we don't expect it to be trend stationary. We consider a constant in the first differences or the short-run part if the original variables have a deterministic trend. For illustration purposes, we will assume a restricted constant specification for the R commands. We will also include centered seasonal indicators because the data is not seasonally adjusted. For Stata commands, we will illustrate an unrestricted constant specification because it does not allow seasonal indicators to be included with restricted constant and no trend specifications. Later in the goodness of fit part, we will check whether our assumptions about the constants and trends are correct or not. Here, we will use 4 variables to analyze the demand for money where LRM represents the M2 definition of money. LRY shows the real income, IBO and IDE are used as proxies to represent the cost of holding money. In Stata, we can use the varsoc command for lag length selection. In the command shown here, we have specified our 4 variables of interest. In addition, we can specify several other options for the command. Here, max lag option allows us to choose the maximum number of lags we want to consider. This means that the command will estimate the information criteria up to 4 lags. It is important to note here that these lags are for the underlying VAR model. The EXO option allows us to include any exogenous variables that we are considering. In our example, we have included seasonal dummies Q1, Q2 and Q3 because the data is quarterly and it is not seasonally adjusted. Therefore, we need quarterly dummies to account for seasonal variations. The number of dummy variables must be 1 less than the number of seasonal periods to avoid perfect multicollinearity. That is why we include 3 dummy variables. It is also important to note here that the dummy variables are not the usual 0-1 dummies. We use centered or normalized seasonal dummies in VECM. In R, the package vars provides the varselect command for this purpose. In the command shown here, Y contains the 4 variables of our interest. The lag.max option here is similar to the max lag option in Stata command. It is used to specify the maximum number of lags we want to consider for estimating the information criteria. The type option here gives us some additional options to specify the constants and trends. We can specify none for no constants and trends. We also get the option to include only constant or only trend. Here, we have specified both to include a constant as well as a trend. The season option here is used to include seasonal dummies. We don't need to generate seasonal dummies on our own here. We simply need to specify the frequency of seasonal period and the software will include the dummy variables. We have specified 4 here because the data is quarterly. If this was monthly data, we will need to specify 12 to include the correct number of dummy variables. The results of these commands will help us in choosing the lags for Johansen's test and VECM. We can choose the lag which gives us the minimum value for information criteria. We can see that SIC and HQIC have a minimum value for 1 lag. On the other hand, AIC has a minimum value for 2 lags. In general, we should prefer SIC and HQIC over AIC for VAR and VECM models because AIC has been observed to overestimate the lag order of VAR and VECM. In our example, however, we will proceed with 2 lags due to autocorrelation concerns. Also, choosing 1 lag for VAR means there will be no lags in VECM and we cannot analyze short-run effects. After deciding the trend specification and lag length, we can apply Johansen's test for cointegration. We will have to specify the number of lags, the constants and the trends here. In Stata, the VECM command allows us to test all the hypotheses of Johansen's test. Like before, we have to specify the variables of interest and choose some other options for the test. The trend option is where we input the trend specification. Remember that we chose to proceed with unrestricted constant specification in Stata, so we will specify constant here. Other options include trend for unrestricted trend, R trend for restricted trend, R constant for restricted constant, and none for no constant or trend. We select the lag length for the underlying VAR model and chose to go with 2 lags for the underlying VAR, which means 1 lag of differences in VECM. The option for S indicators allows us to include seasonal dummies and we specify Q1, Q2 and Q3 like before. Apart from this, we can specify max to report the maximum eigenvalue statistic along with the trace statistic. The option IC will report the information criteria for cointegration ranks. The ERCA package in R provides the command ca.jo to apply Johansen's test. In the command shown here, Y contains our 4 variables of interest. The option type allows us to choose between the maximum eigenvalue statistic and the trace statistic. Specifying eigen computes the maximum eigenvalue statistic and trace computes the trace statistic for the Johansen test. Using the option EC-det, we can choose whether we want a constant, a trend, or neither in the cointegrating equation. Therefore, we get 3 options, none, constant or trend. We have specified a constant in the cointegrating equation here. The option k is equal to 2 here specifies the number of lags in the underlying VAR model. Moreover, we can easily include seasonal dummies using the option season like before. We specify 4 in the season option because we are dealing with quarterly data. The spec option provides 2 different parameterizations of VECM. The long-run option estimates a VECM in the same manner used by Johansen and Giselius. However, this parameterization is not used often these days. We are interested in the transitory option which provides different coefficients for the short run. The long-run part stays the same in both options. In fact, Stata estimates VECM with this transitory parameterization as well. Stata seems to provide relatively more flexibility in specifying trends. The ca.jo command does not give the option to include constant or trend in the short-run part. However, ca.jo has a dumper option that can be used creatively to include trend or exogenous variables. If we look at the trace statistic for R is equal to 0, we cannot reject the null hypothesis of R equals 0 at a 5% level. This is because the test statistic is less than the critical value, indicating no cointegrating relationships. However, when we look at the maximum eigenvalue statistic, we reject the null hypothesis of R equals 0 at the 5% level. According to the maximum eigenvalue statistic, we have one cointegrating relationship or R is equal to 1. This is because we cannot reject the null hypothesis for R equals 1. Meanwhile, the trace statistic indicates no cointegrating relationships. Such conflicting results are common when dealing with real-life datasets. So which one do we choose here? If we look closely at the trace statistic for R is equal to 0, we can see that it is very close to the critical value. This means that we will be able to reject the null hypothesis at a slightly higher level of significance. We will most likely reject the null hypothesis of R equals 0 at a 10% level of significance, or even at around 8% level. As a result, we will proceed with one cointegrating relationship or R is equal to 1. This is because the max statistic indicates one cointegrating relationship at a 5% level and the trace statistic will indicate the same at a slightly higher level of significance. Later in the goodness of fit part, we will check whether this choice was right or wrong. After deciding the trend specification, lag length and the number of cointegrating relationships, we can finally estimate the VECM model with all this information. The Stata command VEC is used to estimate the VECM model. It provides similar options to the earlier VECrank command for Johansen's test. We can specify the variables of interest, trend specification, lags and seasonal dummies just like VECrank command. However, the VEC command includes an extra option to specify the number of cointegrating relationships. Here, we specify rank 1 because we decided to proceed with one cointegrating relationship or R is equal to 1. This will estimate a VECM with one cointegrating vector. The Cajoral's command from IRCA package can be used to estimate the VECM model. In the command shown here, the coint input is the object containing the results of Johansen's test. We use the command ca.jo to apply Johansen's test and save those results in coint. We input that object in this command and we specify the number of cointegrating vectors along with it. Here, we specify R is equal to 1 because we are proceeding with one cointegrating vector. This command will automatically estimate the VECM model with one cointegrating relationship and use the same lags, trends and seasonal indicators we used in Johansen's test. Remember that the ca.jo command does not allow us to include constants or trends in first differences. We only get the option to include constant or trend in the cointegrating vector. Therefore, this command will estimate a restricted constant specification because we only have a constant in the cointegrating equation. In fact, using this command, we can reproduce the exact results reported by Johansen and Giselius in their paper. It is important to note that there can be minor differences in results reported by different software due to different coding. Moreover, each software provides different options. For example, we earlier saw that Stata provides more flexibility when it comes to trend specifications. However, Stata does not allow seasonal dummies to be included in none and restricted constant specifications, which can be done in R. For more flexibility in trend specifications in R, we can also use the VECM command from tsdyn package. In this command, we have to specify the lags and first differences of VECM and not in the underlying var model. That is why we have specified lag is equal to 1. This is equivalent to specifying lag is equal to 2 in the underlying var model. The include option allows us to specify constants and trends in the first differences or short-run part. We can choose to specify none, constant, trend or both. The LR include gives us the option to specify constant, trend, both or none in the long-run cointegrating part. The estim option specified as ML allows us to estimate VECM using Johansen's methodology. However, this command has its own drawbacks. For example, we have to generate the centered seasonal indicators on our own and include them as exogenous variables using the exogen option. The command shown on screen will give the same results as the ca.jo and cajorls commands we used earlier. More importantly, not all combinations of options in include and lr include are possible. For example, if we specify a constant in lr include, then the include option can only be none. So, we cannot estimate the unrestricted constant specification. Thank you for watching, and I will see you in the next tutorial.